Einstein's general theory of relativity says that time moves differently for every person. But why is it like this? We start with two observers and one simple rule. Motion is relative. One observer sits inside a spaceship, the other observer stands still next to distant stars. From the outside, the ship travels at 1,000 kilometers per hour. From inside the ship, the crew feels at rest. They feel no force, so for them the ship is not moving. They can say the area around them is moving. Each observer can treat themselves as stationary and the other as moving. Now inside the ship, someone kicks a ball forward at 100 kilometers per hour relative to the ship. To the outside observer, velocities add in the usual way at these low speeds, about 1,100 kilometers per hour. Both observers agree on measurable events, but they describe motion differently. This classical velocity addition works at everyday speeds because those speeds are tiny compared to light. But one important fact changes everything. The speed of light is the same for every observer. No matter how fast you move, you measure light at the same. That constant value cannot be added or subtracted by ordinary velocity rules. To see how this forces time to change, we use a simple device. A light clock. The clock has two mirrors, one above the other. A single tick is the flash of light traveling from the bottom mirror to the top mirror. Set the distance so one upward trip equals exactly 1 second when the clock is at rest. If the clock is not moving, the light travels straight up. One tick is 1 second. Now place the same light clock inside the spaceship, moving at speed v relative to the outside observer. From inside the ship, the light still goes straight up. The crew measures the same 1 second tick. From the outside observer's point of view, the clock is moving while the light travels. The light no longer goes straight up relative to the outside frame. It follows a diagonal path. That diagonal is longer than the straight vertical path. Light always moves at c, so if it travels a longer path, the outside observer measures more time for the same tick. That result is time dilation. The moving clock's tick takes longer when viewed from the outside. This is also why you cannot simply add velocities for light. If you tried, observers would measure different values for light speed. Instead, space and time adjust so that everyone measures light at c. This has also been proven. A plane was flown a few times around Earth with an atomic clock on board. When scientists compared it to an atomic clock on Earth, it was ahead by 60 nanoseconds. This time difference matched exactly what Einstein's formula predicted. But speed isn't the only thing that can slow down time. Gravity also has this effect. Just think of a car standing on a flat surface. This flat surface is spacetime. If there is no mass and spacetime is completely flat, the car can drive in a straight line. The car takes the shortest and fastest path, a straight line. Now place a massive object, like a planet, in spacetime. The line bends. The car's path is no longer perfectly straight, and it takes longer to get from one point to another. In the same way, gravity bends spacetime. But this bending does not just change distance in 3 dimensions. It changes the flow of time in the 4th dimension, which we can't see. Now, let's get close to a black hole. These objects are so massive that spacetime collapses into these funnels. This is so intense that spacetime is warped almost infinitely. From a safe distance, you would see a clock near a black hole ticking slower and slower. This is because the path the car has to drive becomes nearly infinite. So, if you watched an astronaut entering a black hole, you could see him for years, slowly vanishing. But he crossed the event horizon decades ago and already died. And all this isn't theoretical. We have already measured it. Satellites in orbit around Earth experience time slightly faster than clocks on the ground, because gravity is weaker up there. We even correct GPS systems for this effect, or they would quickly become inaccurate. I hope you understood most of it. If you have any more questions, feel free to ask in the comments. See you.